Modern theoretical neuroscience is largely driven by a single ambition: the search for a mathematical framework that can explain learning, perception, behavior, and life itself. When an interconnected system is forced to carry too much information, it hits a point of structural failure. Theories that try to explain every aspect of cognition often reach this same collapse. The free energy principle, developed at University College London, claims that living systems survive by minimizing surprise. It posits that the brain builds an internal model of the world to reduce prediction error. Researchers at Harvard have pointed out that this optimization principle is so broad it can justify almost any neural data. Because the model and the neural implementation differ in every application, the theory becomes difficult to refute. The original Brain Kinematics Model, or BKM, shared this problem. It attempted to explain all brain activity through strain flow, a concept that became increasingly bloated as it tried to account for every emerging discovery in the field. Scientific validity requires a framework to define what it cannot do. To move forward, BKM has to specify the exact conditions that would prove its core logic wrong. The first step in reclaiming that validity is to stop claiming priority for established mechanisms. BKM assumes that predictive processing, traveling waves, and global workspace theory already work as described. The theoretical landscape is congested. Existing frameworks already describe integration and global access. We strip away redundant variables that neuroscience already measures, like oscillatory phase and connectivity. This winnowing leaves exactly 6 essential BKM entities: carrier medium, texture, strain package, position moment spin, complication, and memory units. Reconstructed BKM functions as a mesoscopic organizational theory. It bridges the gap between abstract top-down principles and the physical reality of neural activity. Survival in this field requires a highly specific mechanistic core. BKM must prove that tracking these 6 variables provides predictive information that current state space descriptions cannot. We have to move past the idea that brain signals travel through a uniform, purely neuronal medium. The brain is a heterogeneous neuroglial network viscoelastic texture. It is a physical environment where the material itself shapes the signal. This texture has 2 distinct layers. The top consists of fast electrical activity, firing neurons. Beneath lies a slower layer of astrocytic fields, regulating energy over longer timescales. Together, they form a coupled system, the medium constantly reshaped by the environment. In this model, astrocytes act as history-dependent transformation operators. Their current state is a reflection of their prior activity, which dictates how they will modify incoming neuronal signals. This establishes the brain's texture as a multi-scale memory layer. The medium's history directly shapes future processing. BKM defines the organized flow moving through this texture as a strain package. A strain package is not a static data point. It is a temporally extended flow retaining its identity even as the underlying neurons change. Each package is tracked by 3 geometric properties: position, its current state of organization; moment, the magnitude of its dynamic tendency to change; and spin, the direction indicating where the package is headed relative to internal boundaries. BKM spin is a geometric indicator of a trajectory. It describes whether a state is moving toward or away from a functional limit and has no relationship to quantum mechanics. Tracking the trajectory and magnitude of these packages provides a map of ongoing transformations that an instantaneous snapshot of neural activity misses. When strain packages interact and lock together into a higher-order relational organization, BKM calls it complication. The brain often generates several of these complicated packages at once, creating a conflict when only one action can be taken. BKM models the basal ganglia as a dynamic trajectory gate, evaluating competing packages to determine which one proceeds to the next stage of processing. Gating happens at specific transition surfaces, selection for cognitive priority, and execution for physical movement. Competing packages approach based on momentum and reward history. The basal ganglia shifts these planes, altering the crossing requirements. The winner crosses to drive output, losers dissolve. Behavior is a result of these shifting internal geometries. The winning signal is the one that successfully navigates the brain's internal transition surfaces. Comparing BKM's mechanical modeling to the free energy principle helps clarify the physical implementation of these abstract ideas. FEP's concept of surprise translates into mismatch-induced neural strain. Here, a predictive model is simply a distributed memory structure stabilizing incoming inputs against an established attractor. BKM differs from standard minimization models by accounting for exploratory strain generation. Tasks like artistic creation or scientific questioning involve the deliberate creation of disequilibrium. BKM treats curiosity as a temporary, intentional increase in organizational strain. Rather than blindly minimizing surprise, brains appear to seek out and structure their own strain to better navigate a complex environment. The next stage of development requires experimental falsifiability. This is the step that moves BKM from a descriptive framework to a testable model. This falsifiable claims matrix grounds the theory in measurable predictions. One of the most distinctive tests involves package genealogy, the history of a package's formation. If we take two networks with the exact same instantaneous neural states, standard models predict they will behave identically in the next moment. BKM predicts that with different neuroglial histories, their trajectories will predictably diverge. Invisible microfissures of history dictate different futures, despite identical present states. If neuroglial texture history does not result in this predicted divergence, the BKM variables should be revised or discarded. A scientific framework only carries value if it is vulnerable to the data. These specific models specify the conditions that would disprove their core claims, and that is where the testing must begin.